we continue our study of data structuring, and we have seen the problem of solving the maximum and minimum of n numbers. Now we examine a second problem, a very similar problem, the problem of finding the maximum and the next maximum of n distinct numbers, that is the largest and the second largest of n distinct numbers. So like the maximum and the minimum, we will go through the mechanism of finding out the largest and the second largest by modifying the program for finding out the largest of n numbers. And let us see what we will achieve if we do it that way. In the largest of n numbers, we initialized the value of max to the first number, and then in the for loop what we did was we read in a number and if max was less than num, then we made max equal to num. That was the simple thing that we did to find out the maximum of n numbers. And in order to find the maximum and the second maximum, we will also take a very similar approach that we took to find the minimum. And I have seen nearly everybody do it this way when I asked anybody for the first time. Next max is equal to max, and here this comparison, if max is less than number, then this is not the only thing that you do. Instead of this, what you do is you first make next max equal to max, and then you make max equal to num. If this is not the case, then this number may be still greater than the second maximum. So what you do is you write an else, and then you write the if next max, else is essential, is less than num, then you just assign next max to num, because max remains unchanged. So this is like this. These two brackets go in together. Please be careful about uppercase and lowercase. They are different in C language. So this is how you would modify the program. That if max is less than num, next max is equal to max, max equal to num. Else, if next max is less than num, then next max is equal to num. Okay, so I have a program for that, and just let's run that program. Which does exactly the same thing. It reads in n here, and then reads in the two values, max and next max. So we assume here that there are more than two numbers, obviously. And the mechanism of initializing those two, I have done it this way, that if max is less than next max, just we swap max and next max. So we have initialized the two numbers. And here is exactly the code I wrote down on that piece of paper, but here there is a slight modification. Since we have read in two numbers, I have done I less than equal to n by minus 2. You could easily modify it to do the other things and put all the checks. Scanf num, if num is greater than max, then next max assign max and max assign num. And obviously you cannot do this statement after you do this statement, then you would lose the value of max. So you must do it in proper order. else if num is greater than next max is assigned num, and simply print the values of print the values of max and next max by this statement. This is the swap routine. So this program is quite obvious that it will work correctly if you give more than 2 numbers. So now let's again go back to paper and pencil analysis to see if you could do anything better. So this is what the core of our program was, and in any case, to do this, if you look at comparisons only, then you are definitely going to do how many comparisons at this point? This comparison will work, and in the worst case you have to do both the comparisons, because actually both may fail and you will have to do both the comparisons. So you will end up doing something like 2 into n minus 1 or 2 into n minus 2 comparisons for finding out the maximum and second maximum of n numbers. The question is, could you do better? Can anybody has any suggestions of what to do? Again we will go back to how max was solved, and we will see whether we can do anything while solving max to get the next maximum. And the whole solution structure of finding out the maximum of n numbers, whichever way you work it out, actually inherently lies in that tournament structure. So let's take any tournament of 1, 2, 3, 4, 5, 6, 7, 8 numbers I have taken, and this is the tournament to find the maximum. Now while finding the minimum, we compared only the losers. Now is there any key observation to find out the second largest? Can 4 be the second largest? The person who is the second best player in this tournament must have lost to the best player sometime. That is the core idea. The second largest must definitely lose to the largest in a comparison. Otherwise he is not the second largest. You cannot declare a person winner by unless he has defeated the second largest person somewhere along the tree. For example, here the second largest will occur between this fellow, and this fellow. Must occur. The second largest must occur among those people who have lost out to the largest. This is an absolute key observation, and these are the necessary and sufficient items which are to be compared to find out the second largest. That is, you have to compare among the losers those who lost to the largest in the tournament, and among them you find out the maximum. You will get the second largest element. For example, here between 1, 8 and 9, if you find out the maximum, you will find the second largest element. The rest are unnecessary to compare. So we come to the key observation here. The second largest element must necessarily lose to the largest element in the tournament. Point number 1. And now we come to the question of optimizing. The second largest element can be found by comparing only those elements who lost to or were compared to the largest. Along the tree, now not only at the first level as in the max and min, in the max and min we were satisfied by first time losers, but here it is not first time losers. You must have lost somewhere in the full tournament. And what do we want to do? Finding out the maximum of n numbers will require n minus 1 comparisons. We must minimize this set to find out the second largest. So how will we minimize this set? Depends on how we set up the tournament. This is one case of this set, as we just saw. If we solve it like we solved our maximum of n numbers, the program which we just saw previously was something like this, isn't it? We went along like this. This was not the tournament. The tournament was skewed. Even this was compared with this and this was compared with this. In this tournament, if we set up a tournament like this, then these are the elements which are to be compared because they have lost out to the maximum. If it is like this, then only these elements have to be compared. This one, and this one. Leaves, it's not necessary that leaves have to be compared. Now can you tell me what decides the number of elements that are to be compared to find the second largest? The path is decided by the path of the winner. The length of the path of the winner decides, that is, how many tournaments the winner has to play decides how many opponents that person played with. So you have to minimize the number of tournaments that the winner has to play. Now you don't know the winner a priori, therefore in the worst case, if you put in a tournament like this and the winner was here, then all the others would have to be compared. Therefore, the length of the path of the winner in the tournament decides it. And now the length of the path of the winner can be the longest path in the tournament. Therefore, in the worst case, the longest path in the tournament can decide the number of elements which are going to be compared to find the second largest. Therefore, your idea of minimizing the set to be compared for the second largest is to set up a tournament in which the length of the longest path is minimum. Therefore, we come to the solution, that is the observation in which the solution is to be obtained. In the worst case, the number of comparisons to find the second largest is equal to the length of the longest path in the tournament, in the worst case, because that may be the path of the winner. Therefore, the length of the longest path of the tournament is minimized, must be minimized, and we say that it is minimized when the tournament tree is balanced. What do we mean by balanced? There are many meanings of balanced, but for our tournament structure, let us argue it this way. If we set up pairwise comparison at the leaves and then pairwise comparison, if we continue to do pairwise comparison as is done in a standard tournament, you will see that if there are 2 to the power n numbers here like 8, for example, if there are only 2 players, then there will be only 1. If there are 4 players, the length of all the paths will be 2. If there are 8 players, then you can set up the tournament by playing only pairwise so that the length of the path will be 3. That is, you can make n players play in such a way that the length of the path will be k such that k is the smallest integer which is just greater than, such that 2 to the power k is just greater than or equal to n. In other words, the length of the path, the length of the longest path can be reduced to this value. The ceiling, that is the largest integer, or the you round off this or you truncate plus 1, truncation of log n to the base 2 plus 1, which is called the ceiling, that it is the next integer which is closest to n. So if you balance, we will come to balanced trees and balanced tournaments much later on, but let us understand it that if we play it pairwise here and then pairwise here and then pairwise here and continue, we are just going to get the minimum length of the longest path. And if we get the minimum length of the longest path, then all we have to do is compare amongst the losers. Among the losers who lost to the winner, that's all we have to do. So this is the idea of solving the problem. Now we have to get it down to programming. That is, are we going to store up this structure? Because unlike the maximum and minimum, where we could just put them into arrays very simply, we do not know the winner till the complete tournament is finished. Therefore, only when the tournament is over can we know who is the winner, and only based on that can we decide on who are going to be compared in the next phase. So we have to set this structure up. That is, we have to implement the result of the tournament somehow. We not only have to store these n numbers, we have to store this structure. That is, now we have the data structure tournament. Which was not so obvious in the previous case, but here we are now reached a situation in which we have to implement this tournament structure, which we conceptually drew up with circles and links. So the question is, this is the data structure which we have in mind. The next phase is, how do we implement it? So we come to the next question, how to implement a tournament structure. We can put our red element, these are the elements 8, 7, 15, 1, 6, 9, 4, 3 into an array. And then we can set up the tournament. Without going into much more details, I will quickly go into the solution, because I do not want to start discovering how to set up the tournament. But if you have some idea about numbering, then you will see, suppose I did a numbering like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Let's see this numbering. The comparison, now suppose my red in elements are put in array locations 8, 9, 10, 11, 12, 13, 14, 15. Then the comparison of 14 and 15 goes into 7. The comparison of 12 and 13 goes into 6. The comparison of 10 and 11 goes into 5. The comparison of 8 and 9 goes into 4. The comparison of 4 and 5 goes into 2. The comparison of 6 and 7 goes into 3. The comparison of 2 and 3 goes into 1. So now do we have a mechanism of knowing exactly where the comparison of two elements will go into? If two elements are in locations, we have made sure that two elements which are to be compared are in consecutive locations, point number 1. And the result of their comparison goes into that index which is half of their index. 8 by 2 is 4, 9 by 2 is 4 if you do integer division. Similarly 10 and 11 by 2 is 5, here 14 and 15 by 2 is 7, 6 and 7 by 2 is 3, 4 by 2 or 5 by 2 is 2, 2 by 1, 2 or 3 by 2 is 1. So if we put our elements here, then we can easily set up the tournament structure in an array. So if we have got n elements and we declare and we can put them out in an array of size 2n minus 1. We can easily build up the tournament in an array of size 2n minus 1. Okay, so how do we build up the tournament in an array of size 2n minus 1 is the next question. So we'll rework the example. How do we start? Where do we start with? We can compare these two. So we read in the elements and we store them. Suppose you are reading in 8 elements like we did here. We store them from locations n to 2n minus 1. So when we have read in 8, we'll start storing them from 8 to 2 into 8 minus 1. We'll just store them first. So we'll read in these elements and we'll store them. 8, 7, 15, 1, 6, 9, 4 and 3. And then what we can do is we can compare these two and put it here, compare these two, put it here, compare these two, put it here, compare these two, put it here. And then do from here to here, compare these two, put it here, compare these two, put it here, and then compare these two and put it here. A much more easy way of doing the whole thing is if you start backwards. You compare these two and put the larger here. 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 And just continue. Compare these two and put the larger here. Compare these two and put the larger here. Compare these two and put the larger here. So for I equals to 2 star n minus 1 right up to here, in one loop you can simply set up the tournament. Is that okay? So now this is an example with 8 elements, which is the power of 2. Let us just do another example which is not a power of 2. So we have got 1, 2, 3, 4, 5, 6, 7 elements. So n is equal to 7. So 2n minus 1 is equal to 13. So in our array we have got 13 locations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and say 13. The first thing that we do is store the numbers from 7 to 13. 8, 7, 15, 1, 6, 9, 4. And then start backwards. 9 and 4 will be put in 6. So 9 is put here. 1 and 6 is going to be put in 5. These two are going to be put here. Now note, since it was an odd number, there was a problem, but that problem is taken care of. These two are going to be compared, and this is going to be put here. These two are going to be compared, and this is going to be put here. These two are going to be compared, and this is going to be put here. You get a slightly different structure compared to the tournament that we would have set up, but this is also a tournament. So doing it this way will give you the full tournament structure set up. Now once you have the tournament structure, you know which is the largest. Now what do? Now how do you find out the second largest? Suppose you've got more than 2 elements, okay? Then you start between 2 and 3 and you initialize the second largest to the smaller of the two. Now go to the larger of the two. If this index is 2, so if this index is 2, then jump to 4 and compare these two. The smaller of the two must be compared with the tentative second largest. So first you start with 15 and you initialize the second largest to the smaller of these two. So you keep a variable called next, say, which is initialized to 9, and index I is made 2 because this is larger and this is smaller. Then you make I is equal to 2 into I, and so I becomes 4. Once I is made 2 into I and I becomes 4, now compare 4 and 5, I and I plus 1. The smaller of the two is compared with this. That is, smaller of the two is 8 is compared with this. The index of the larger of the two is doubled to find out the other two locations. So we first compared with, we saw these two, compared with this one. Then we came here, jumped, found out the other two which are to be compared, saw this one, and then again we jumped and saw this one. So we compared 9, 8 and 11, and we compared these two obviously again and again, and we compared these two and we compared these two. So we made no more than some 2 into log of 2 to the base n comparisons. And with this indexing and setting up of the tournament, you can easily find the largest and the second largest. The largest will be at the head of the tournament and the second largest can be found by a routine. So let's quickly see how the program of finding a tournament and finding out the largest and second largest look like. No, I'll come to it. So what we will do is, we have declared an array for the tournament. This is a program which just sets up the tournament. It does not do anything else. So today we will just see how to set, we'll see the program of setting up a tournament. This will have large implications in solving other problems as well. So we will visit this tournament again in the next class. So we read in n, then we read in the n numbers and stored, as I said, from n to 2n minus 1 in the array tournament. So initially the n elements are stored from locations n to 2 star n minus 1, as I mentioned. So that's where you read them all into. And what is the loop? The loop starts from the end, so it starts from comparing, initializing I to 2 star n minus 2 as long as I is greater than 1, and at each step you are comparing pairwise and moving back, so the loop control is I equal to I minus 2. And what you do is, you put the turn I by 2 index to the maximum of turn I and tune I plus 1. That's what we were doing when we did it by our own hand calculations. For example, first the index 2n minus 2 and 2n minus 1 will be compared, and the maximum will be stored in that I by 2. Then I will become I minus 2. So if there were total of 8 elements, then we would have started comparing 14 and 15. The next we would have come and stored it in 7. Next I would be I minus 2. So we would have compared 12 and 13 and stored the larger of 12 and 13 in 6, and continued till I continued as long as I is greater than 1. When I becomes 1 or 0, we stop. So this is how you just set up the tournament. And this maxi program, it just takes a very simple thing. It finds out the maximum of 2 numbers and returns the larger number. That's what it did. It took 2 numbers and returned the maximum of 2 numbers. So let's see how the setting up of the tournament works. So let's give, say, 4 elements. So we've given 4 elements, 3, 1, 2, 4. They were stored in locations 4, 5, 6 and 7. 2 and 4 were compared and 4 was written here. 3 and 1 were compared and 3 was written here. 4 and 3 were compared and 4 was put here. So this is how we got that result. If we run it again with, say, n equal to 5, and you give a simple data 1, 2, 3, 4, 5. So from 5, 6, 7, 8 and 9th location, these values were stored. 4 and 5 were compared and 5 was stored here. 2 and 3 were compared and 3 was stored here. 5 and 1 was compared and 5 was stored here. 5 and 3 was compared and 5 was stored here. So whatever you give, you are going to get back the value of the tournament. We'll stop here today for you to just digest what we have done to the tournament. Try and work out the program to now, given such a tournament data structure, how we are going to find out the second largest. And we shall revisit the tournament next day, see the exact code for finding out the second largest, and see the ramifications, see what else we can do with this. And we shall visit this in more details, because though very simple, this structure has got a lot of very interesting properties and helps to solve some of the core problems much better than what you could have imagined them to be.